Where does the data used by weather forecasters such as air temperature, relative humidity, and pressure originate? Until the arrival of satellite measurement capabilities, all data came from thousands of weather stations located across countrysides around the world and on buoys that are stretched out and scattered over the oceans. Today, satellite observations provide 24-hour coverage of the globe, including the continental United States. With the recent advances in satellite technology, we can obtain fine-scale detail of clouds and various weather systems as shown in this animation and image. Data originating from both satellite observations and ground-based measurements are merged through complex computer algorithms, and this information is typically processed in weather maps as shown in the following image. On these weather maps, we can determine the location of high and low pressure, the location of fronts, and other large-scale weather phenomena. The four main constituents of weather include temperature, wind speed and direction, humidity, and air pressure. Before starting our experiment, it is important to define each term. Simply put, wind is the air in motion. To describe the wind properly, we must discuss its speed and its direction. There are many ways to determine the wind speed and direction, but a snapshot of the wind across a large area can be determined by examining cloud motion on satellite, seen in this image. Wind is ultimately caused by differences in atmospheric pressure, which can be defined as the weight of the air above any location. Air flows from areas of high pressure to areas of low pressure in an attempt to balance the pressure between those locations. Therefore, greater differences in pressure tend to result in faster winds. To understand the concept of temperature, we will use the following animation here. For a gas, temperature is a measure of the average speed or motion of its air molecules. As shown in this animation, as the temperature decreases, the speed of the molecules decrease with it. And as the temperature increases, so does the speed of the molecules in the container. There are two measures of moisture that we can use in the atmosphere. The first is known as absolute humidity, which is a direct measure of atmospheric moisture. And the second is known as relative humidity, which is a measure of how close the air is to saturation. As shown in the animation, as the temperature of the air approaches its dew point, the relative humidity will increase. And this is because as the temperature reaches the dew point, the air is saturated. So to put this all together, when we talk about weather, we are describing a daily snapshot of the atmosphere at a specific time. So the goal of this video is for students to analyze atmospheric data so that they may determine how variations in temperature, humidity, pressure, and wind speed relate to each other. And that will enable them to understand specific weather conditions. So using a wireless weather sensor, students will learn how, 1, changes in pressure can have effects upon temperature and vice versa. 2, they will learn the relationship between temperature, relative humidity, and pressure. And 3, the idea here is to examine the relationship between precipitation and the pressure and temperature changes that tend to follow it. So before we start the automated part of this experiment, where we would use a Pascal wireless sensor, it may be useful for some students to receive their measurements using physical equipment that corresponds to each measurement. So it may be that some students may want to measure pressure directly, temperature, precipitation, or etc. And that means it's useful to describe in a number of ways how each of these instruments would work. Let's suppose a student wants to take measurements of pressure. Then probably the best instruments to use, which would give you a direct measurement of pressure, would be your aneroid barometer seen here. Now, this aneroid barometer is something that can be hung up in a classroom or in any other location. And this is useful because it means that you could take a long time series or a long period of measurements over an entire day or perhaps over an entire week. So it may be helpful to give a sense of how to put this together. So first, what you would do is to hang this aneroid barometer that you see here in its permanent location. The reason why is that every movement of the barometer, if you move it back and forth, may begin to give subtle changes to the reading that occurs with your actual barometer here. So once the set pointer has been fixed, don't move the barometer, hang it in place. Next, the barometer must be set to show the air pressure at your specific elevation or altitude. The official barometric readings for your region will give you the mean sea level pressure for your area. And this is usually something that you would hear if you listen to a TV weather forecaster, or if you listen to a radio forecaster, or if you go to the National Weather Service and look at your specific location. At that point, note the time of the official reading as well as the reading itself, so you can check your barometer at the same time of day that the official reading was made. So if the set pointer, if this pointer that you see here is different from the official reading, you may need to reset and recalibrate your pointer. Now, if it is the case that you live more than, say, 50 or 100 miles from an official recording site, that means I would suggest that you would take a reading on your barometer at either 9 a.m. or at 3 p.m. because those would be consistent with what you would see at other stations as well. Now, in terms of adjusting your pointer, for this particular barometer, what you see here, the pointer is controlled on the back side, as you see here. And on the back side, you have a little screw right there. And that little screw is going to be used to turn, and that's going to adjust the actual barometer. So that means you're going to need a screwdriver and use the actual little small screwdriver and use that to slightly move the actual pointer and set it to the barometric pressure that corresponds to your altitude at your specific location. Now, once you have set your barometer correctly, then you can use the actual gold knob that is right here in the front to move the red pointer directly over the black set pointer. So that means the idea would be to first adjust the back side that you see here on a small pointer, and then you would use the big pointer right here to make sure that it's right over that location. So that means your black mark is going to be your set, and then you're going to measure deviation from that with the smaller pointers seen here. Now, question becomes, how does this aneroid barometer work? An aneroid barometer has a metal capsule that's inside here with flexible sides, and that capsule should contain a small amount of air. As the air pressure increases, the capsule walls in here is going to squeeze and contract. And even the slightest change in the air pressure will change the thickness of the capsule. So as the atmospheric pressure increases, the capsule's volume of air gets squeezed and compressed. And thus, to record the change in atmospheric pressure, one end of the capsule is fastened to a pointer by a series of levers and pulleys. So as the volume of air inside the capsule changes, the pointer will move. And that's how you have deviations between high pressure versus low pressure. Now, the National Weather Service reports its air pressure at Earth's surface in terms of inches of mercury typically. Now, this barometer is looking at everything in terms of millimeters of mercury. So that means there will have to be a conversion between those two system of units if you want to use them. And that system, that conversion can be found easily online. Air pressure above the Earth's surface is reported in millibars, or sometimes called hectopascal. Now, if you look at this particular instrument, notice you have millimeters of mercury, mmHg, and you have hectopascal, which is the same as a millibar. And that is the way that this is typically reported if you're using the National Weather Service. Now, another thing a barometer can do, it can also show changes in altitude. So that means, roughly speaking, the barometer scale goes down about 3 millibars for every 25 meters of ascent rising motion. So in other words, if the barometer scale reads 1,020 hectopascal at sea level, and you travel 300 meters up a mountainside, the scale will then read somewhere around 980 millibars by the time you reach the top of the mountain. Now the question becomes now, how do you actually use this barometer to actually detect weather changes? Now, this is a general statement, but it actually can be pretty well verified for most types of weather. Bad weather is usually connected with low pressure. That will be true except in coastal regions. The barometer itself will show whether air pressure is falling or rising. And from that, you can tell whether a high pressure or low pressure is moving into your area. The same thing would be true regarding fronts. Fronts will typically have pressure changes associated with it. So that means you can use your barometer to detect whether or not a cold front or warm front is moving in your area. Now, it's important to keep in mind the actual daily reading itself is not as important as noting the changes in air pressure. So you can assume that the weather for your area is changing if there is a change greater than about 7 millibars or 7 hectopascal within 24 hours. In the summer, air pressure gradually rises over a 2-week period and then remains steady until the weather begins to change. Thus, if the barometer begins to fall suddenly with falling pressure, that means a violent storm will be approaching your region. Now remember, although you have a barometer that measures pressure changes, a barometer does not predict the weather. It monitors weather as it is currently happening. The other part here is that the weather patterns that you see around you are usually closely linked to wind direction, temperature, the time of year, as well as the air pressure. So by recording the daily reading of your barometer over a period of time, you will be well on your way to understanding weather forecasting, as well as weather observation and monitoring. Another tool that will be very useful for students if they wanted to track weather and to examine the relationship between different variables would be a standard rain gauge. Now, there are many different types of rain gauges with various types of sensitivity. So this rain gauge, for instance, as you look upon here, you essentially have inches on the large side seen here, and you have centimeters on the other side seen here. And this particular rain gauge has a spike at the bottom so that you could plant this into grass in a particular area. Now, at any sort of National Weather Service station that you will find across the country, there are different types of rain gauges, and the idea is that you get more and more precise based upon the equipment. But one thing that a student can do, and this is done a lot of places around the country, is that you can confirm or test the accuracy of your own rain gauge if you decide to buy one or if you decide to make one. In this case, what you can do is that you can take this and place this around your house or around the actual school. What this is going to teach you is some important facts about rain collection across the United States. For example, it matters where a rain gauge is placed in order to have accurate interpretation of the rain in a given area. So you can imagine, for example, of taking multiple rain gauges and putting them in different locations around a building or around your house. And what you will find is that the actual accumulated rain will vary from location to location based upon where you are. And the fact that you have this sort of fluctuations, or the fact that you have inconsistent measurements, tells you that the actual collection of rain is much harder than simply just taking a rain gauge and putting it in the ground. What I would suggest for students is to try this out with 3 or 4 different rain gauges and pick a 2-week period of time in which you can measure the rain falling and look at the actual accumulated precipitation for each rain gauge and to see if they match. From there, you can ask questions of whether or not the accumulated rain is more accurate at one place or another. And you can also say with certainty whether or not some locations are basically overestimating the actual rain or perhaps underestimating the amount of rain that's there. Now, the final instrument that we would have would be your standard thermometers here and here. Now, thermometers are just like any other instrument. This is a mercury thermometer. And for a mercury thermometer, the basic idea here is that you're trying to get the mercury in the column to rise or to fall based upon the heat that is coming to the bottom or to the bulb of the thermometer. Just as in a rain gauge situation, where you place a thermometer matters in terms of the reading that it will obtain. And this is because for most areas, the temperature is not going to be constant. Whether you're looking at a large area such as a town, or you're looking at a smaller area such as a few houses or even a school, you will see that there are slight deviations in temperature around the school, and the actual location of where you place the thermometer matters. So this is something else that can also be done. You can take thermometers like these and you can place them at different locations around your house or around your school, and you can measure what the corresponding temperature changes will be, and you can see whether or not the thermometers give consistent results. And what you will likely find is that as you go to different locations and you place this thermometer at different places, you will get situations in which you have shading, which will tend to reduce the actual temperature or underestimate the true temperature. Or you may get a situation where you're close to a parking lot or to concrete or some other area, and thus your thermometer will overestimate the actual temperature. So what we're going to do now is that I've done a series of recordings with my aneroid barometer seen here, with my rain gauge seen here, and with my thermometer here. And now I'm going to show you some results that I've done by watching weather change over time in my particular region. So when discussing the experiment that I performed, I want to rehearse what I mentioned previously. What I decided to do was to measure the pressure, the temperature, and the precipitation over a period of days using physical instruments. So for example, I'm using the aneroid barometer that I mentioned before, where this was hanging in my house, and I did this over a period of about 10 days. Second, I used 3 different rain gauges to measure the actual precipitation, and I placed them at different locations. So the one that says rain gauge number 1, I placed this about 5 feet from my house so that it was not obstructed by anything in view. And then I used a second rain gauge like this and placed it near the gutters of my house. And then third, I placed a third rain gauge on the opposite side of my house, away from any other obstruction. And then the last thing is that I took my thermometers, seen here and here, and I used one thermometer and I took measurements that were under a shaded area. So that is going to be the temperature number 2 that you see there. And then I took another thermometer and put it out in the open sun, and that's temperature number 1. And what I did is I measured all of these variables twice a day from September 1st through September the 10th. And what I did was to record the values to see, could I use these instruments to see if there's any sort of relationship between temperature, pressure, and the precipitation. And I measured these at approximately 9 a.m. and 3 p.m. each day. And these are the results that you see in front of you in terms of the reading. Now, starting first in my temperature column, what you should notice here in terms of observations is that there is a clear day to night cycle that is seen in the data. So notice starting from September 1st, going down through September the 10th, you have a fluctuation on temperature that in the morning is in the 70s and the afternoon is in the 80s. And that is the first broad pattern that you can see with my data. And if students repeated this experiment, they would see the same idea. They should see a day to evening cycle when it comes to temperature as the first observation. The second observation is that the fluctuations in temperature is going to vary, and you can kind of see how that temperature fluctuation seen here compares to the precipitation readings over here. So notice that for each of the rain gauges that you see, times in which you had more rain that was present, you tend to have a reduction in temperature. And times in which you did not have rain that was present, you saw that the high temperature went up to the upper 80s. Now, that should not be fully surprising, but it does prove, in this sense, in terms of the data, that there is a relationship between the expected precipitation, or the precipitation that fell, and the actual temperature. In terms of the science, the background behind this is whenever rain falls over a long period of time, some of that rain will evaporate, and evaporation tends to cool the air down as a whole, and that tends to lower the temperature at that particular location. And that's what you broadly see with the data. The second thing that you can see here is that there are fluctuations when it comes to measuring temperature at different locations. So notice that the first thermometer that you see here is consistently recording higher values than the second one. And that it's not completely surprising because the second thermometer was taken in a shaded area, whereas the first thermometer was taken in the open sun. And therefore, to reemphasize the point, where you actually take your measurements will dictate the actual readings that you have. It did not change the pattern between day to night temperature cycles, and it did not change the pattern between temperature and precipitation. But notice that the temperatures disagree with one another just based upon their location. The next part is the rain gauges. And again, the rain gauges were placed at different locations around the house. 2 of the rain gauges were placed in regions in which there are no obstructions, and 1 is placed next to gutters where there would naturally be some obstruction to precipitation. And what you can see is that rain gauge 1 and 3 match very well. And notice that rain gauge 2 is consistently underestimating the actual rain. So, as you would expect, that means that if you want to get an accurate assessment and counting of the precipitation, you need to have this removed from obstructions. Now, this column here that says NWS precipitation, this is the actual recorded precipitation given by the National Weather Service in Charleston for the day and time in question. So the way that this precipitation was measured for the National Weather Service is that they take their precipitation reading at the beginning of the hour and watch it accumulate towards the end of the hour. So that means for the National Weather Service, the 9 a.m. recording is based upon taking the precipitation from about 7:57 a.m. up to about 8:56 a.m. And this is similar to what I did for each of these. I looked at the precipitation over the entire range up to that point. So that means for the 3 p.m. reading that you see here, the 3 p.m. precipitation is based upon taking all of the accumulated rain from 9:01 a.m. up to about 2:58 p.m. And notice that the values are pretty similar. And the main difference is in terms of the sensitivity of the instruments. Now, if you recall, this is the way that the actual rain gauge looks. And it's very hard to probably see this clearly. But note that the gradations that exist is pretty small. I can get a precision up to about 1/10. So that means I can do 3.1, 3.2, 3.3, and etc. And that's why you see that everything is more or less rounded to the 10th place, unless I see explicitly that is basically 3/4 of something. In contrast, the National Weather Service can get precipitation to be accurate up to the 100th place. And hence you have 2 decimal places that you see here. So that means a normal rain gauge that you see here, when you're using good measurements and you're actually putting this in the right location, you can actually get a result that is quite similar to what the official National Weather Service reading will give you. And hopefully this is something that students will be able to see when they do their own measurements with a rain gauge like this. The final point is to ask the question, how does the pressure relate to everything just stated? Well, one of the things I want you to see is that there is a relationship between pressure and precipitation. So for example, notice that the precipitation generally increases right after the precipitation occurs. And notice that when stormy weather is coming, such as in this period, the actual pressure is going down. Now, this is harder to see because there is a day to evening cycle associated with pressure. And so you're meant to see that there's a day to evening cycle also combined with the change in pressure that happens just by precipitation. But in terms of the science behind it, after precipitation happens, after it rains and there's evaporation, as I mentioned, evaporation tends to cool the air. So therefore, as the air cools, it should become more dense than its surroundings, and therefore air should be sinking towards the ground, and that will tend to lead to higher and higher pressures after precipitation occurs. Now, coming up to the point where the system is changing, where you have a warm day to say a stormy day, you'll probably see the opposite change in terms of precipitation. But the point here is this is something that every student can do in terms of their own recording of data. That it's very easy to hang this object in your house or in any location and watch the actual readings. It's very easy to take a rain gauge such as this and to plant it within the ground and to do measurements at the same time each day. And using a thermometer, we can measure the actual temperature to a good bit of precision. And so a great experiment for students to do will be to repeat something like this, but for their local area. And what they will see is that there are relationships between the onset of storms and precipitation with temperature and precipitation readings. We will now set up our Pasco wireless weather sensor. So as a reminder, the wireless weather sensor is an all-in-one instrument for monitoring complex environmental conditions. It's a very small detector, as you see here, not very large, but it houses several sensing elements within this single unit. And you're actually able to produce 19 different measurements associated with this small device that you see here. Some of the common measurement instruments would include, there's a thermometer there that gives you the temperature of your environment. There's a barometer inside that is electrically used that gives you the barometric pressure. When you attach the wind vane, as you see here, it allows you to obtain the wind speed and wind direction. And there's a humidity sensor on here, which means that you can obtain relative humidity. So those would be the major variables that you can get from here. And then because of the actual technology, you're able to take these variables and use them to obtain other variables that is often used in meteorology. So for example, if you have the temperature and the wind, you can actually compute the wind chill if it's a particularly cool day. Likewise, if you have the temperature and the relative humidity, you can compute what the heat index is, or what we call the heat stress index. Now we will look at the procedure that we're going to use to set up our device. So the very first thing that you will need to do is to connect and to charge. What this means is that your device comes with a USB port cover to the right. And so if you look to the front and then turn around to the back, notice that there's a USB port right there. Now, with that particular package, you're going to have a micro USB cable so that you can connect your wireless device to a USB port or USB charger. Now, just in terms of a background here, if you pull this out of your box for the first time, it will take around 2 hours or so for this to fully charge if you have a good wireless station. So make sure you leave time to charge this completely. Then after you charge it for a few hours, then you're going to turn it on. And as you see, there's a button right in the center right here, and you're meant to turn that on. And when you turn it on, what you will notice is that you will see the GPS light and the Bluetooth light comes on, and it will flash back and forth like so. Now, since it's flashing back and forth, this is meant to tell you that the device is now ready to pick up Bluetooth and is also ready to be connected to the GPS part of the sensor. The next part is, once you have it turned on, we're then going to switch to looking at the data collection side of our software. Now, I'm going to go through this in more detail, but the main point here is that you need to make sure that you have Bluetooth capability with your computer so that you can actually use the software. So now we're at the data collection aspect of the software. Now, the software I chose was named SparkView, and SparkView comes directly from the website from Pasco. So if you were to search for the wireless weather sensor, it will give you software that's either SparkView or Pasco Capstone. For this, I'm going to be looking at SparkView. Now, just in terms of a basic experiment, the first thing you want to do is to go to the sensing data aspect here and click on it. And we'll ask you to connect to a device. Now, if you press and hold your device and turn it on, what should pop up would be a device that is connected to your Pasco wireless weather sensor. Now, the 6 numbers you see here is the ID number of your particular detector. So for mine, it is 018690. So if you click on that, it will begin to connect to the actual device via the Bluetooth. And then the next thing it's going to ask you to do is, how would you like to proceed? Now, I've already done at this point some original data logging, so I'm going to delete my data from this and move on. But this goes back to the many different variables that you can observe as this goes on. So let's suppose I want to observe temperature, relative humidity, and pressure. Then I would click on those 3 that you see here. And then the next thing that will go is I'm going to go to graph, seen here. Now, right now, the way that this is set up is that you have temperature, relative humidity, and barometric pressure on the bottom. Now, if you wanted to change the units to that, say edit data properties, you can click on that tab, and what's going to pop up would be temperature and degrees Celsius to that. You can change this to Fahrenheit if you like, and the same thing is true for the barometric pressure. You can also change this to millibars, which is the common units that is used when pressure is reported in meteorology. For right now, I'm just going to keep those as they are. Now, right now, this is reading 24.8 degrees Celsius, relative humidity 42.4%. This is reading what is currently going on in my location. Now, once I press the start button, it's now going to start recording that data and placing it on a graph. And as you see, it's just recording this second by second. So you can begin to see changes in the actual temperature, changes in relative humidity, and any changes that are going on with the pressure. Now, what you will see here is that the actual relative humidity is changing a good bit, while the temperature and the pressure is remaining constant. Now, this is something to be expected because relative humidity depends not only upon the moisture that is in the air, it also depends upon the temperature. And if the temperature fluctuates slightly between, say, 0.2 degrees or 0.3 degrees, that's going to have an impact upon the relative humidity. Now, let's suppose at this point you want to stop and record your data. And you can press stop right there. Now, if you go over, you have different sorts of tabs here that can give you ways to set up your hardware as well as other experimental tools. Now, what I'm going to do here is that now I'm going to run an experiment in which I take multiple different sensors and place them in different locations around my building to get different amounts of data. And one of the points here to see is that there are going to be slight changes in all of these variables just based upon where these things are located. Now, to conclude this video, what we're going to do is to discuss some simple variations that you can do to change the experiments we've done and to track certain types of weather. So the first variation would be to use your weather instruments, whether you're using the physical instrument itself or the Pasco weather wireless sensor to track a cold front. Now, this is something that if you wanted to do, it's probably helpful to look for a forecast in which a cold front is going to be present. And then from there, we would just go through the basic science behind which a cold front should develop. So as a cold front moves into a region, warm air, as you see here, is moving from the south, and cold air is advancing towards the warmer air. That means as you read your actual temperatures, you should get a sharp decrease in temperature as the cold front passes, a change in the amount of precipitation present, but there will also be a substantial change in the pressure as it passes by. Another variation to do is to track a warm front. And again, this will be helpful if you have a forecast for when a warm front would pass through your area. So as we track a warm front, this would be the opposite type of process, where in this case, the warm air is the part that is moving forward and is moving towards the cooler air, seen by the red and blue arrows that you see there. So as the warm front passes by the specific region, what you expect to happen is that there will be clouds and precipitation forming ahead of the warm front boundary, and therefore you will see changes in precipitation, changes in the local temperature, and as the warm front passes by, you should expect there to be a change in temperature increasing. It should be cold ahead of the warm front and warm behind the warm front. And then you can use this same principle to track any sort of weather system if you have a forecast.